In this module of WAVE, we want to learn about highway geometric design. Specifically, by the end of this lecture, you should be able to describe the role of geometric design and how it interacts with safety and efficiency. You will be able to identify the main components of roadway alignment, most importantly, horizontal and vertical alignment. You will be able to interpret stationing and understand the stationing and how it is connected between horizontal and vertical alignment. You will be able to recognize key terminology related to both horizontal and vertical alignment. You will be able to explain safety concepts, especially with regard to stopping sight distance on curves. And finally, you will be able to identify common horizontal curves, different types of that, and different elements related to horizontal curves. With that being said, if we look into the philosophy of geometric design, as I just explained a few minutes ago, I mentioned two keywords when I started our learning objectives. Those two keywords were safety and efficiency. So these are the two themes that stand out when we think of the highway geometric philosophy, the design of the geometry of highways. In terms of safety, the most important thing is people being able to see objects in a timely manner, to see hazards in a timely manner. It's better to say that. Imagine you are driving on uphills, and as soon as you're going up, suddenly you see an object is left on the other side of the curve. A safe design should provide enough time for you to react to that potential hazard on the roadway. And that reaction, it could be just complete stop because the entire roadway could be blocked and closed. So we have to provide that opportunity for drivers to stop. We will talk a lot about that. We'll learn about stopping sight distance, both on vertical, if you're going up hills or down hills, or if you're on horizontal turns. We will talk about them. There is also passing sight distance that is less significant compared to stopping sight distance because we always have the option to make passing prohibited, but stopping is critical safety issue, and we have to be always we have to be cognizant about how we are providing that in our design. When we talk about efficiency, there are different things to consider, like human factors. You know, actually, the geometric design, one of the challenges of the geometric design is that there are so many factors, so many determinants that are interacting with each other, and we have to measure their interaction at the same time. Like drivers, what is most comfortable and efficient for drivers? I'm sure, excuse me, I'm sure you have all been on roadways when you're driving and it feels like roller coaster. That is definitely not, a comfortable situation for the design. And we are always struggling between what is feasible and what is ideal. But still, we have to find a point. We have to find a balance point that is safe for drivers. It is also comfortable for them. So we'll talk about that. We'll see how different like reaction times or what is a comfortable deceleration rate for drivers. We'll talk about them. We should also consider the design vehicle. Sometimes a passenger car might be a critical vehicle. Sometimes it could be a truck. Sometimes it could be a fire truck that should be accommodated in our design. And finally, we have to think about the design environment. If I'm designing for interstate highway versus when I'm designing a very remote rural road, the expectations, the design criteria is going to be very, very different. Now, it is important to notice that, this is going to be a very complicated interaction and it could be a semester-long topic to just talk about geometric design. Here we are going to focus on very fundamental introductory level design, and we will just pick some examples from each one of these factors that are involved in highway geometric design. The source here is a policy on geometric design of highways and streets. This is a national standard that you must follow. It is published by the American Association of State Highway and Transportation Officials, very well known as AASHTO. And at the time of recording of this lecture, the most recent version that is published is the seventh edition, published in 2018. And this book, in traffic engineering and transportation engineering, this is very well known as AASHTO Green Book, or just the Green Book, because of the cover that has been, for a while, it's been a green cover. Now, in design of highways or roadways, you could be held accountable if you do not follow AASHTO guideline. This is very important. You probably have seen these billboards next to the highways or freeways that if you got into a crash, let us know. Part of that is a crash could happen because of a poor geometric design. And if they look into the geometric design and see that the AASHTO guidelines were not met, then you could be held accountable for that. So there is a real urgency to understand AASHTO process and procedures and how to design highway geometry. When we talk about highway geometry, or we talk about highway in general, as you're driving on a roadway, you're moving in a three-dimensional environment. So at the same time, you're moving on X, Y, and Z. But for the educational purposes, if I want to teach you highway geometry, also for construction purposes, if I want to create some maps and give it to the construction company to construct the roadway, 3D images are difficult to understand and difficult to learn, right? So what do? We turn these 3D environments into three two-dimensional environments. So what are these two-dimensional environments? The first one is what we call plan view or horizontal alignment. Imagine I look at the roadway from an aerial image and just a Google image and see how it is moving on the ground. That would be a plan view. Another view is what we call profile view or vertical alignment. This time, what I will do is that I will cut the roadway at the center line. Imagine I have a roadway, two lanes going different directions. I will cut the roadway at the center line. I'll go and stay aside and I look at how this roadway is moving alongside the natural ground. That would be a profile view or vertical alignment. I could also look at the cross-sectional view. It means that I will cut the road perpendicularly, and I look at how this roadway look like again compared to natural ground if at some points we need excavations, if at some points we need embankments. We can find that out based on cross-sectional view. For the purpose of this workshop, and given the time limits that we have and the importance of this topic in autonomous vehicle area, we think that horizontal and vertical alignments are most related. So I'm gonna only talk about these two alignments. I'll start with vertical alignment and then we'll finish with horizontal alignments. But you could ask the question that, okay, if I turn this into two-dimensional. For now, let's just think about plan and profile. How can I connect these two together? So I have two sets of maps, and I need to find a reference point that allows me to connect these two sets of maps with each other. How do we do it? We use stationing and later elevation of the points. So we identify the station of points both on horizontal and vertical alignment. In US units, every station is 100 feet. So we start from an origin. Let's say there is an origin that is 0. And from that point, every 100 feet is going to be one station. Like the example you see here, for example, a point that is 685.3 feet from the origin would be a station 6 plus 85.3. So we define stationing in that way, and we define it both for horizontal and vertical alignments to connect them with together. Just for your information, if you ever happen to work with metric units, in metric units, every um, station would be 1 kilometer. Now, there is one distinction here to be made when we are talking about stations on horizontal and vertical alignment. What is that? When I talk about horizontal alignment, stations are defined along the roadway. So you see that, imagine this is the center line of the roadway. This is that plan view, right? And we are measuring the stations along that horizontal alignment, along that plan view. But for vertical alignment, we measure the stations along the projection of the curve, not the curve itself. Even the length of the curve, when we talk about the length of horizontal curves, we are talking about the arc, the length of this arc that exists here. But when we talk about the length of vertical curves, we are talking again about the projection on the x-axis. So this is the main difference that exists between the stationing on horizontal and vertical alignment. With that, let's talk about some fundamental topics, most important topics in vertical alignments. Any vertical alignment is identified by three main points: PVC, PVI, and PVT. So let me talk about these vertical curves. First of all, you see that there is a plus G1 here. This is what we call initial tangent. So a vehicle, imagine this is uphill. A vehicle is going up with a grade of G1. In geometric design, whenever you're going up, grade is going to be positive. Whenever you're going down, grade is going to be negative. So you're going up, and this is initial tangent, and we want to connect it to another, to a final tangent. And in order to make it safe, in order to make it comfortable, we use this vertical curve here. Now, this curve, wherever it starts, wherever the curve starts deviating from that initial tangent, we call it PVC, point of vertical curvature. So mainly the beginning of our vertical curve. Wherever this curve goes back to that final tangent that you see here, so the end of the curve, we show that with PVT, or point of vertical tangent. And the place that these two, the initial and final tangent, intersect with each other, we call it PVI, or point of vertical intersect. It is very important in geometric design to find the station and also elevation of these 3 points. For construction purposes, it is very important to have that information. And given that we are on vertical curves, elevation plays a very important role here. Again, as you see, as I explained earlier, length of a curve is measured not along the curve itself, but on the projection of the curve along the x-axis. And we could have different types of curves depending on what is the composition of the initial and final grades. Those compositions are mainly going to be categorized in two different types of vertical curves that we call them sag curves and crest curves. So as the name suggests, sag and crest. Now, if you want to find a technical difference, the technical difference is that for crest curves, PVI, point of vertical intersect, is going to be above the curve itself. So as you can see in all these examples, of the crest curves, we have the PVI on top of the curve. And for the sag curves, we have the PVI below the curve, the vertical curve itself. The design, especially when it comes to the safety, is very different when we talk about sag curves versus crest curves. What is that difference? We will talk about it in a few minutes. What else is important to know about vertical alignments? In order to create a safe and comfortable transition on vertical alignments, it's been shown that parabolic curves, a parabola, would work the best. So vertical curves, we never use circular curves to connect two tangents. We use parabolic curves because of that safety and efficiency that we talked about it earlier. Now, parabolic functions are y equals ax squared plus bx plus c. So we have to be able to define this equation for every one of the curves that we have, which means that I have to find a, I have to find b, and I have to find c. By the way, what is x and what is y on this equation? So y is showing the elevation, and x is showing the station or just the distance measured from PVC. So what was PVC? Beginning of a curve. So from beginning of the curve, we can find the distance and elevation, x and y. In other words, we can find that for every one of our vertical curves. So in order to find the values of A, B, and C, if you find, for example, the first derivative, put that equal to 0, so on and so forth, these are the three parameters of a parabolic curve used as a vertical curve. A would be the difference between the two grades divided by 2 times of the length of the curve. B is just going to be G1, whatever it is. If it is positive, it's going up hills, it's positive. It is going downhill, it is negative. And C would be PVC elevation. So kind of when we are using this equation, Y, all the Y's are going to be relative to whatever was the elevation of the beginning of the curve. Uh, Another important thing is that when we talk about geometric design and vertical alignments, we could consider different combinations of the grades. But one type of curves that are more frequently used, and we are only going to focus on those types of grades, is what we call equal tangent vertical curves. What does that mean? Equal tangent means that PVI is exactly halfway through the curve. So if I go back, for example, to this slide, you see that what is drawn here is that this is the length of the curve from PVC to PVT, and PVI happened to be exactly at the middle of this length. This is what we call equal tangent. But look at the other example. For this one, it doesn't seem that PVI is exactly at the middle of the distance between PVC and PVT. So this is not an equal tangent vertical curve. The equations that I'm going to show you in the remainder of the lecture today, they are all going to be based on equal tangent vertical curves. Now, let's talk about stopping side distance, because I told you a few minutes earlier that when we talk about safety, the most important thing is to provide that stopping side distance. So when you are driving on a vertical curve, it is important to make sure that if there is a potential hazard on the other side of the roadway, we are able to see it. Now, of course, we would love to make that as wide as possible so you can, like a flat roadway at 0% grade, you can see everything in front of you. I wish it was always possible, but we are always dealing with limited budget. So I cannot do that. Therefore, I have to figure out what would be a minimum length that is still going to be safe. So that is the most important part. We are going to find out what is the stopping side distance and how can I find a minimum length for that curve that will provide that stopping sight distance. Now, if I have more budget, if I can make it longer, that's fine. But I cannot go below that minimum value because that is what is going to provide the minimum stopping sight distance. Now, when we talk about stopping sight distance, imagine you are driving with a speed of V, initial speed of V, and you want to come to a complete stop. So you are driving and you see an object on the other side of the curve and you want to stop. This is basic physics. So the time that it takes for you or the distance that it takes for you to come to complete a stop, it is basic physics. Look at this equation. Stopping sight distance, it has two terms. Let's start with the second term. Second term is how far do you travel while you are still perceiving and reacting. So you see that according to AASHTO's suggestion, if it is unexpected, which is the case in, when you're doing highway geometric design, that reaction time is 2.5 seconds. What does that mean? It means that if you're driving on a rural road, you're going up and you suddenly see an object on the other side of the roadway. On average, it takes 2.5 seconds for people to perceive that, oh, something is wrong, and I need to react to that. So during that time, they are traveling with the speed of V1, the initial speed. So that would be the distance that they are going to travel. If you watch our traffic signal timing, the lecture that is related to traffic signal timing, the reaction time that we used in that example was 1 second in that scenario, in that case. Why? Because when you are driving on urban streets and you're approaching a signalized intersection, at any time, at any moment, you expect the signal to change, right? You are driving and signal turns to yellow and then red. That is not equal, that is not equivalent to when you're driving on that rural road and you suddenly see that a tree is broken on the other side and the entire roadway is blocked. These two things are very different with each other. We consider that difference in the reaction time. And then the rest is how long it takes, or what would be the distance that it takes for the vehicle to now come to a complete stop based on the initial speed and also based on the impact of grade. So if you're going upgrade, the grade is going to help you. If you're going downgrade, the grade is going to be negatively impacting you. But given that it is a curve, one side is going down, the other side is going up, right? So in order to consider this trade-off and stay on the safe side, usually when we are calculating stopping sight distance, we assume level grades. So we usually find SSDs based on the G to be 0. Because when we're talking about vertical alignment, one side is going up, the other side is going down. So these two could interact with each other and neutralize each other. And also, when we consider G, we seems to be on the safe side in our design, more conservative side in our design. So mostly we go with a G of 0. Then there is a deceleration rate of 11.2 feet per square second. That is considered comfortable, efficient in, for highway geometric design. So based on this equation, if I know let's say speed limit, this is the design speed, but there is a difference between design speed and speed limit. But let's just keep it simple and say that this is the speed limit. Based on the speed limit, I can find out that what is the stopping sight distance. For example, people need to see an object 500 feet before they get to that object so they can safely and conveniently come to a complete stop. Now my job is to design that curve in a way that SST is provided, that 500 feet, for example, is provided on that curve. Now, how do we do it? We do it differently for crest curves versus sag curves because the condition is very different here, right? When you are on crest curves, the curve itself is blocking your view of the other side because you're going up, you don't see the other side. But when you're on sag curves, because you're going down, you can see technically the objects on the other side. But there is a challenge there. What is that challenge? We will talk about that in a few minutes. But for now, let's just talk about the crest curves. So imagine this is a crest curve vehicle going up hills, PVC, PVI, and PVT. And we want to design this length of the curve such that this driver would be able to see the object, a potential hazard on the other side of the roadway in a timely manner. There are two different conditions based on the characteristics of a parabolic curve. One is if S is less than L, and the other one is if S is more than L. What does that mean? This is very important. S and L are two different concepts. You may be able to see the end of the curve, or you may not be able to see the end of the curve. That is not an issue. The issue is being able to see an object, to see a potential hazard on the other side of the roadway. So with that being said, if we assume that S is less than L, that you cannot see the end of the curve, then you have to design a curve with this equation. This is the minimum length of the curve. A is the absolute difference between G1 and G2. SSD is what you calculated in previous step, basic physics, right? And H1 and H2, H1 is the height of driver's eye, and H2 is the height of the object on the other side. This is based on math, just the geometry of parabolic curves. We can find this equation. What if S is more than L, which means that you can see the end of the curve. And now, if you want to find the minimum length of the curve, you will obtain a different equation for that. And definitely one of these two assumptions is correct, right? It is either S less than L or S more than L. So what we do in design is that we always start with S, with assuming S is less than L. We calculate L, and then we check whether that assumption was correct or not. If that assumption is correct, we're good. If not, we move on to the next equation that you see here. Again, I want to emphasize that these are L and S, two different things. One is talking about the length of the curve. This is what I have to design. The other one is S. This is what I got from from physics of a vehicle driving with a speed of V and wants to come to a complete stop. AASHTO Green Book provides some suggestions for the values that you saw in those equations. Like they suggest H1 to be 3.5 feet. So a driver's eye to be 3.5 feet above the ground. This is a sedan, right? We do not design for trucks here. Why? Because trucks are not critical vehicles here. A truck driver is sitting higher on the roadway, so they actually have a better visibility of a potential hazard on the other side of the roadway. So they are actually in a better condition. They are positioned better compared to a driver of a passenger car, a shorter car. So the critical vehicle, the design vehicle here would be a passenger car. Then for H2, we consider that to be a small object, a 2 feet object, something like maybe a dead animal, or maybe a box or a broken tree that is left on the other side of the curve. So if we use these values, considering that A is also, as I said, absolute difference between the grades, and we replace them into the equations that we got from parabolic curves, these are the two equations that will be obtained, and these are the equations that are used to design vertical curves. So based on a stopping side distance, we will find the minimum length of the curve. We check whether this assumption was correct. If it was correct, we are good. This is the length that we should provide. Otherwise, we move to the second one and we find the minimum based on this second equation. And then this should be something that we provide. We cannot go below this minimum length. Now, let's say that for some reasons, I cannot provide this minimum length of the curve. There are some existing conditions, like there is a bridge, there is some infrastructure in place that prevents us, or there is actually a curve already in place that it just doesn't meet the requirements that we have. What should we do? First option is to fix the roadway, to fix the design. But if it is something that is not possible at all, then we may think of reducing the speed. That would be another option, because if you lower down the speed, what happens is that it brings the SSD down, stopping side distance down, and it will help with the minimum length of the curve. So one of the reasons that sometimes, especially on vertical curves, you might see a reduction in the speed. I'm not talking about horizontal curves yet. On vertical curves, one of the places examples of seeing a reduction in speed would be just to make sure that we have enough time and opportunity to come to a complete stop because of a hazard. Now this was everything about crest curve. This was stopping side distance on crest curves. What about sag curves? What if you are actually going down and we want to think of a potential hazard on the other side of the roadway? What is important here is nighttime condition, not the daytime. Because during the day, you can just bring your head up and see if there is anything in front of you, right, on the other side of the curve. What is problem is that during the night, as you are driving down hills, the lights are gonna illuminate just an area in front of the car, not necessarily an area on the other side of the roadway, of the curve itself. So we have to figure out that what area is illuminated in front of a driver and then figure out how to design that curve. And now, while I'm talking about these things, given the objectives of our workshop, I would love you to think about how the design for a machine driver is going to make a change on all of these items. Like when I'm talking about reaction time, when I'm talking about where is the height, what is the height of driver's eye? Now what would be the height of the camera on your car? What would be the height of sensors, lidars, whatever that you're using to detect the objects? That would play a role in this design, right? So as I'm talking about these different design elements, and you see that this is all based on human drivers, I would like you to think about how a machine driver is going to change the story here. Now, let's get back to our the stopping side distance on sag curves. So we have to know that distance that would be illuminated, and that distance depends on the height of the headlight and also the angle of the headlight on the cars. So if a car is going down on this sag curve, again, I'm trying to figure out what would be this appropriate length to provide an appropriate stopping side distance. This stopping side distance is the same as before. It hasn't changed. Remember, I told you we mostly find the stopping side distance values for highway geometric design using G equal to zero grade. So in order to stay conservative. So that value would be the same for the same speed on the sag curves and crest curves. Now on the sag curves, if S is less than L, the equation that will be obtained based on the characteristics of a parabolic curve is here. You see that we have H, that is the height of the beam lights, and we have beta, that is that angle that is illuminating in front of the car. And if S is more than L, we will use another equation to calculate the minimum length of that sag curve. AASHTO has some recommendations, AASHTO Green Book, some other recommendations for the design here. Assumes the headlight to be 2 feet. Again, we are designing for a sedan, for a car that is lower on the roadway, 2 feet. And assuming the beta to be 1 degree, there are two equations. If you replace these numbers, the equations for a sag curve will turn into this. So we usually again start with SSD less than L. We calculate minimum length of the curve. We check the assumption. If it is correct, if that assumption was correct, we are good. Otherwise, we go to the second one, and then we'll make sure that that length of the curve is provided in our design. This was everything about stopping sight distance. But what about passing? If we want to provide passing opportunities on our roadways. Now, passing opportunity is only related to two-lane highways because in order to pass a slow-moving vehicle, you have to occupy the opposing lane. And that opposing lane, there could be cars coming your way. So we have to make sure that now you have enough distance of the vehicles that are coming in the opposite direction to safely go back to your lane and to make a safe decision, pass the car, and then go back to your original lane. With that, this PSD, passing sight distance, is generally much longer because of the uh, players in this game, right? When we were dealing with stopping sight distance, there was a moving car and a stationary object. Now, I have a moving car that I want to pass it, and there is also another moving car that is coming my way. So because of these three factors, passing sight distances are generally much longer than stopping sight distances. And it's not a requirement to provide passing sight distance. We are always able to prohibit passing on vertical curves. And it actually happens a lot of times. Rarely, if we have a two-lane highway, we would allow passing on vertical curves, sag or crest curves, especially on crest curves. Uh, but we know that if passing sight distance is provided, for sure stopping sight distance is also going to be provided. But that would be what I can call a luxury of a vertical alignment. AASHTO makes some assumptions here. It assumes that vehicles are all moving with constant speed. It is, of course, on the conservative side, right? Because when you're passing a slow-moving vehicle, we tend to accelerate, right? To go faster to pass that car. It assumes the difference is more than 10 miles per hour and assumes the driver's eye is 3.5 feet. Again, kind of a conservative value for where is the location of eye to see another vehicle on the opposing lane. With that, AASHTO considers four main elements, components of passing. What are those four components? D1, that is the distance that you are making a decision to start the passing maneuver. D2 is the distance that you are occupying the opposing lane. D3 is the clearance distance. What would be that clearance distance between the passing vehicle and the opposing vehicle? And then D4, which is the distance that was actually passed by the opposing vehicle. So a safe passing sight distance should provide enough opportunity for all of them. D1 plus D2 plus D3 plus D4. So a passing sight distance should provide a distance more than that. Opportunity to see objects in more than that in longer distances, so we would be on the safe side. AASHTO, based on the characteristics of parabolic curves, based on some assumptions that we saw earlier, suggests these two equations to find the minimum length of the curve that is required to provide PSD. And PSD, again, it is something related to speed. So based on the speed, design speed, we can find the PSD. There are tables in AASHTO, and based on that, we can find minimum length of the curve. We will always start with PSD less than L, similar to what we did with SSD and L. This was everything about vertical alignment, not everything about vertical alignment. This was one drop in vertical alignments, but just an introduction to vertical alignments. And let's make sure that you also receive some information, introduction about horizontal alignment. What was horizontal alignment? That was the plan view. So if I have that aerial image of the roadway, looking at the roadway, how it's moving on the natural ground, on the ground, that would be our horizontal alignment. We just learned a few minutes ago that when we are talking about vertical alignment, the most appropriate function, mathematical equation, would be a parabola. A parabolic curve is the most appropriate one. For horizontal curves, it is circles. Circles are the most common forms, and simple circular curve is one of the common options. I am actually, whatever you see in the next slide is based on a simple circular curve, which means that there's only one radius. So imagine I have one tangent here and another tangent here, and I want to connect these two tangents using the curve here. This is just a simple circular curve with one radius. We also have reverse curves, as you can see here. Most often when I have two parallel roads, look at the laser point here. If I have a roadway like this and another roadway like this, and I need to connect these two. So you're going this way, and now you need to connect it to a roadway like this. We usually go with the reverse curves. Each one of them is just a simple circular curve. We also have compound curves that they are comprised of two simple circular curves, and we have spirals that R is changing. Uh, this is most close to a natural driving. So when you're usually driving, navigating the turns, horizontal curves, it's been shown that drivers pick various radius as they are going through the curve. So if we want to design exactly similar to the way that drivers drive, that would be most close to a spiral curve, which means varying radius for these circular curves. Here, we want to only focus on simple circular curves. Now, let's look at different parts of a circular curve. Similar or equivalent to what we had on vertical alignment, that was PVC, PVT, and PVI, we have 3 points that shows start, end, and intersect. So PC, or point of curvature, this is the start of our curve. So there is an initial tangent. By the way, I hope that you have already changed the dimension in your brain, because we are now talking about plan view. This is no longer a profile view. This is a plan view. So this is the tangent, initial, final tangent, that we are connecting them with a circular curve like this. As you can see, the length of the curve this time is measured along the curve itself, not along, there's no projection here. We are on the x-axis. So PC is the start of the curve, PT, point of tangent, is the end of the curve, and PI, point of intersect, it is the intersect of the two tangents. We have a radius here from some center. We have some other important measures, like we have delta, central angle of the curve. We have T, which is the tangent length. Very important information to find stations. If we want to find stations along the curve, one of the important things to consider is T. We have E and M. E is external distance, and M is middle ordinate. These are important information with regard to stopping side distance. In just a few minutes, we will talk about them. And L, I already talked about it. Based on the characteristics of a circular curve, we can easily find the values for each one of these main features. Like what would be T? T is R tangents of delta by 2, right? E, M, L, and also another thing that is D, that is called degree of curve, angle subtended by a 100 feet arc along the horizontal curve. These are the things that we can calculate based on the characteristics of a circular curve. Now, how is this useful? Because for any horizontal curve, I have to figure out what is the required radius. Like when I was talking about vertical alignment, we had to figure out what is the required length of the curve. For a horizontal curve, what is important information is radius of the curve. So the equation that we should develop, equivalent to what we had before, now is to find a minimum radius that will provide a safe and convenient and efficient transition on a horizontal curve. When we talk about that, the most important thing to consider is vehicle cornering. So as you are driving on a horizontal curve, the centripetal force is applied to your car and it wants to throw you out of the roadway, right? That is why we make the roadways elevated. This is something that we call super elevation. Depending on what is the speed and some other conditions, we will just elevate this edge of so bank here and elevate the edge so we can fight with that centripetal force using the friction of between the tire and the roadway and also using the weight of the car as another factor. And it's very important to make sure that there is a balance here. So as the vehicle is moving, this shouldn't be too high to drag the vehicle inside or the vehicle to be thrown away out of the curve, or even if it's a slippery road or icy road, the road slip downward. So it is important to make sure that there is a balance here. If you put these forces equal to each other and try to create that balance, this is the equation that you get. So if you want to balance all those forces, a minimum radius required is v squared, whatever is the design speed, times that gravitational force times the friction that exists between the tires and the pavement and the super elevation that we designed. So super elevation, typically it's somewhere between 4% to 10%. And you can use this, or AASHTO also has some tables that suggest the minimum radius to be used for different speeds and for different super elevation values. And there's also a limiting value of friction that is a function of the speed. So for the same speed, you see the same limiting values of the friction. Like if I am designing a roadway with 65 miles per hour, and I'm applying a 6% super elevation on the roadway, the minimum required radius is 1,660. So that should be provided. Now, if I have more budget to make a wider, bigger radius, that's totally fine. But I cannot go below this because this is based on those forces zeroing out and to keep the balance of the vehicles and provide that safe and comfortable transition on the horizontal curves. We can also talk about safety on the horizontal curves, but from a different standpoint. You know, when you were going up on a crest curve, that we talked about it a few minutes ago, when I was going up a vertical crest curve, the curve was blocking me from seeing the other side of the roadway. But when you are driving on a horizontal curve, there is no such a thing. What is actually blocking your view of the other side if is any obstruction that exists here. So imagine that there are trees in this part. Imagine there are buildings, there are billboards, there is a hill here. So those are the things that would block your view of the other side. Because this is now the critical lane, right? So if I look at if I want to find the obstructions, this is the critical lane. If you're on the other side, if you're on the other lane, you have a better visibility. You can use the road as a buffer to see the objects on the other side. But this way, the most inner lane, this is the critical lane to find to find a stopping sight distance. So what do? We assume that a driver's eye is at the center line of the innermost lane. And then we assume that this arc is one safe stopping sight distance. With that, we will find the area here, this middle ordinate, that must be cleared. So I repeat that again. I will assume that the driver's eye is at the center of the innermost lane that is traveling. Let's assume that there is an object on the other side that is blocking the roadway, and I want this driver to see that in a timely manner so they can come to complete a stop. In order to do that, this part should be cleared. This is what we call middle ordinate, and it must be visually cleared so drivers can see a potential hazard on the other side. Now, for that, there are there are two different ways to approach it. One is that if I have the stopping sight distance, how can I find stopping sight distance? Exactly like before. Basic physics. You're driving with a speed of v, you want to come to a complete stop. Let's assume g to be 0 to be on the conservative side, safe side. So I have the SSD, and based on that SSD, and if I have the radius, I can find the middle ordinate. Or if I have the middle ordinate, I know how much clearance exists at the edge of the roadway, and I have the radius, then I can find out what is the stopping sight distance provided on that curve. And if this stopping sight distance is more than the minimum stopping sight distance, we are fine. Otherwise, we have to do something about it. And that do something about it is, first of all, remove the obstructions. If you need to cut the hill, if you need to remove trees, billboards, buildings, do that. If that is not possible, then we have to lower down the speed to make sure that we have a safe condition of transitioning on that horizontal curve. This was also a very, very basic introductory level, introduction to horizontal curves. There is much more left, but I hope that it will give you enough insights and enough idea that when you're thinking of autonomous vehicles and, the different detection technologies, how it could relate to the geometric design. These were our references for this lecture.